Thank you very much, all of you, for coming today to listen. I hope that I will speak clearly enough that you can understand. If not, please ask some questions when we are finished. So today I want to talk a bit about variations along the Sunda Subduction Zone. Okay, so this is the area that we will talk about today. Specifically, this red line is showing what I call the Sunda Trench, going all the way from eastern Indonesia through Java, Sumatra, up through the Andaman Islands and into Myanmar. Just a short description of where I am getting my experience from in this area. This little island right here off West Sumatra is called Nias Island. During my dissertation time, I spent about 4 months, 3 different times, 1975, 76, 77, doing field mapping of the structures and stratigraphy on that island. In 1977, I joined a cruise from Scripps Institution of Oceanography around the island of Nias. We went back again in 1980 and did a survey using seismic reflection off the central part of Java, came back up and surveyed more around the area of Nias. Recently, I was able to join during the International Geological Congress a few years ago, a field trip to the Andaman Islands, where I was able to see some of the geology there. And during probably about 2011 to 2015 or so, I was able to join Lin Tuong for field work around Ramri and Chetuba Islands here in Myanmar and along the Tandoi coast. So in terms of understanding the Sunda Subduction Zone, the seaward-most part, I think I have some experience doing that. The areas that are of interest to us in the entire system that are going to be affecting everything that we talk about in the Sunda Trench actually starts up here in the north in the Bay of Bengal with the Bengal Fan. The 90 East Ridge serves to bisect the Indian Plate into the western side and the eastern side, sediment coming down through down into the Bengal Fan and into the Sunda area is mostly what we're going to be talking about today. We'll talk about the area offshore Java and Sumatra, the Andaman Sea, Andaman Islands. One thing that is important in our discussion of the tectonics of this area is the subduction vector. In eastern parts of the Sunda Subduction Zone, subduction is pretty much perpendicular to the trench, about 7 centimeters per year. That changes to the west off Sumatra about 6 centimeters per year, 5 centimeters per year off western Sumatra, and then off the Andaman Islands about 4 centimeters per year. The direction of convergence is pretty close to the same all along here, and that means off Java we have perpendicular subduction. As we go through Sumatra, the subduction is oblique until we get further up to the north where it's highly oblique, and then even strike slip motion along this part of the system and on it up into Myanmar. So that difference in subduction vector is something that is very, will be helping us or hindering us in our understanding of the tectonics of this area. The location of volcanoes in this region, in the eastern side of the Sunda region, very many volcanoes all the way up through Sumatra. Once we get into North Sumatra, the volcanoes are quite sparse, and not too many of them through the Andaman Islands and up into Myanmar. When we look at the seismicity, in the eastern part, the red dots are the shallowest, as we can see here, orange, light blue, and dark blue going to the deeper depths. So in the eastern part of the system, there are earthquakes that go down as much as 700 kilometers. The subducting slab shallows under Sumatra, coming up into the area of the Andaman Sea. There's a zone of seismicity in the back arc region, also along the subduction zone, and then it becomes a little bit more diffuse along the southern part of Myanmar, and we pick up the slab again at intermediate depths in the northern part of Myanmar. I'm going to show you next a little block diagram through the central part of the offshore Sumatra area through my favorite place, Nias Island. This is Nias here on the surface. We can see outboard the subducting plate coming in cross-section. There are earthquakes that are outboard of the trench. Mostly, this is the plate that's bending on normal faults as it bends over and fractures going into the lithosphere. There are what we call megathrust earthquakes along the subduction zone underneath the area, such as Nias, and these are the dangerous ones that cause very large earthquakes and tsunami. Overall, the important thing in understanding the tectonics has to do with India, which has been moving northward, colliding with the Sunda area called Sunda land here over the past probably 50, 60, 70 million years. This is a quick diagram put together by Claude Ranjan a few years ago that shows overall the motion of the Indian plate from about 73 million years ago, moving up to the north at about 10 centimeters a year until about 45 million years ago when the collision first started. Subduction slowed down, collision slowed down to about 4 centimeters per year. Notice in his diagrams, he shows Indo-Burman ranges tacked on to the eastern side of India. There are many different kinds of reconstructions that people have done that have Myanmar in many different places, and I will show you another one in a couple of minutes. And what we're going to do is look at a diagram, a series of reconstructions that just came out earlier this year by Advocat and van Hinsbergen. They have divided up the Indian Ocean into many different plates. You can see the result of the overall motion as we see it today. So we have Myanmar east of India. Australia is the other part of the Indo-Australian plate. And this big zone in purple, they are calling, and many other people have called, Sunda land. Again, 90 East Ridge is an important area. This area up here, northern part of India, or just north of the Indian continent, is called Lhasa. This is quite important because it's an area that has been the site of collision for maybe 50 or 60 million years. And we'll talk about the importance of that as we move through the system. So we'll jump back to about 215 million years ago during the Triassic, where we can see Burma, West Burma, it's called in this reconstruction, sitting not south here where India is, but way up north of the present, or the continent of India, over towards Lhasa. Sunda land over on this side. So West Burma is here, India, Australia, Antarctica, the main continents that are going to break up and start to move northwards. Lhasa is sitting here with a subduction zone on this side of it. The entire Indian plate is eventually going to move to the north to collide with Sunda land. And we'll take a look at what happens during that collision process. So again, here is West Burma. This is now a time of 150 million years ago, separated at the north between India and the Tethys Himalayas. So there's a spreading center in between. Lhasa, by this time, has moved well away from the Himalayas. It has a subduction zone over on this side. Subduction zones all the way north of Lhasa, which is going to allow for collision before about 100 million years. So by this time, 100 million years ago, during the Cretaceous, the Lhasa terrain is sitting up here, already collided with the Asian mainland. Myanmar sitting down here in the middle of this huge ocean with a subduction zone on one side, transforms on either side, many different zones where there's subduction. Things that we're going to be talking about later on, the Andaman ophiolite is a piece that, according to this reconstruction, has been in place along what they're calling the Woyla Arc, now Indonesia. Myanmar, West Burma is eventually going to slide past, rotate around, and collide in here over the next 60, 70 million years. So there's subduction zones all the way around. East Java is now sliding up to collide over in this area. So here we are at about 50 million years ago. By this time, India and Myanmar are now in contact. There is subduction going on along this part of the margin. The Andaman ophiolite is along this piece of a subduction zone. So there are nested subduction zones here going along the boundary of Sunda land and over to the west. Again, the Andaman ophiolite is sitting on this subduction zone. 45 million years ago, things are still rotating. India is still moving northward. Continuing at 40 million years, 35, 30 million years ago. By this time, West Burma or Myanmar has made complete contact with Sunda land, is now colliding there. The Andaman ophiolite is now south of that block, and India is well into its collision time. Continuing on to 25 million years, 20 million years. By this time, the Andaman ophiolite is south of Myanmar. 15 million, 10 million, 5 million, and here we are again at the present. So again, India with its collision zone in the north, Myanmar sitting in here between Sundaland and India with the Andaman ophiolite down to the south. What I want to do now is back up a little bit to 30 million years ago. So this was the time when the collision was really getting going in India. There apparently was a bit of a seaway between northeastern India and the West Burma terrain. So the collision is ongoing at this time. And what I want to do now is to bring up a different sort of reconstruction for this time period that was done by some sedimentologists, people who care not only about the big collision, but about what the sediments are doing. So at 30 million years ago, they call it the Eo-Himalayan stage. By this time, the main Himalayan belt is rising due to the collision. It's shedding sediment off to the east, and we have the predecessor to the Bengal fan starting to form. Another rock unit, the Andaman Flysch. These are sedimentary rocks of this age, 30 million years, that are exposed in the Andaman Islands. By the time we get to 15 million years, again, the Himalayas are really eroding at this point, dumping lots and lots of sediment out into the Indian Ocean, forming the Bengal fan. The 90 East Ridge is already here, causing a separation of this sedimentary terrain. Some of the sediment is going off to the west, and then other sediment off to the east. And this is our area of the Sunda Subduction Zone that we'll be concentrating on today. So by the time we get to the present day, we have a huge amount of sediment out in the main part of the Indian Ocean in the Bengal fan. But we also have another little lobe over on this side called the Nicobar fan. It doesn't have nearly as much thickness as the Bengal fan, but it has enough that it is affecting the subduction zone. So let's take a look again at our topographic features that we care about here.